Mathematics 9. Week 3 and 4.
Good day, everyone! Once again, this is Teacher Jenny welcoming you to our Mathematics 9 class. Our topic for today is the continuation of quadratic equations and functions. We will deal with the characteristics of the roots using the discriminant, relationship between the coefficient and the roots of a quadratic equation, writing a quadratic equation given a pair of solutions, and transforming equations to quadratic equations.
Topics: Unit A, quadratic equations and functions. 1.1 Roots of quadratic equations using the discriminant. 1.2 Relationship between the roots and coefficients of quadratic equations. 1.3 Finding the quadratic equation given the roots. 1.4 Equations transformable to quadratic equations. Key terms: roots of quadratic equations, coefficients of quadratic equations, sum of the roots, product of the roots, discriminant, equations transformable to quadratic equations. General objectives. What you will learn: in this module you will characterize the roots of quadratic equation using the discriminant. Describe the relationship between the coefficients and the roots of a quadratic equation. Write a quadratic equation given a pair of solutions. Skills you will use: in this chapter you will use the discriminant to determine the number of real solutions of quadratic equations and solve equations transformable to quadratic equations. Why is this important? The discriminant of a quadratic equation tells the number and type of solutions. It serves as a double check when solving quadratic equations by any of the four methods. Discriminant. Definition. 1. The radicand b square minus 4c in the quadratic formula is called the discriminant. 2. The discriminant of a quadratic equation tells the number and type of solutions. It serves as a double check when solving quadratic equations by any of the four methods. 3. When using the quadratic formula in solving quadratic equations, consider calculating the discriminant first. Using the discriminant. Given a quadratic equation in the form of x squared plus bx plus c equals 0, where a, b, and c are real numbers and are not equal to 0, we can determine the number and type of solutions of a quadratic equation by evaluating the discriminant b squared minus 4c. If b squared minus 4c greater than 0, the equation has two real solutions. Both will be rational if the discriminant is a perfect square or irrational, if otherwise. 2. If b squared minus 4c equals 0, the equation has only one solution, which will be a rational number. 3. If b squared minus 4c less than 0, the equation has no real number solution. Examples. 1. Use the discriminant to determine the number of real solutions of 16x squared minus 8x plus 1 equals 0. Solution: b squared minus 4c equals negative 8 times 2 minus 4 times 16 times 1, replace a to 16, b to negative 8 and c to 1. 64 minus 64. b squared minus 4c equals 0. Because the discriminant is 0, the equation has only one real solution. 2. Use the discriminant to determine the number of real solutions of x squared plus 2x plus 3 equals 0. Solution: b squared minus 4c equals 2 times 2 minus 4 times 1 times 3, a to 1, b to 2 and c to 3. Equals 4 minus 12. b squared minus 4c equals negative 8. Because the discriminant is negative, the equation has no real number solution. 3. Use the discriminant to determine the number of real solutions of 2x squared minus 3x equals 4. Solution: b squared minus 4c equals negative 3 times 2 minus 4 times 2 times negative 4, a to 2, b to negative 3 and c to negative 4. Equals 9 plus 32. b squared minus 4c equals 41. Because the discriminant is positive, the equation has two irrational solutions. Example 2. For the equation 3x squared minus 8x plus c equals a. Find c, so that the equation has only one rational number solution. b. Find the range of values of c for which the equation has two real number solutions. c. Find the range of values of c for which the equation has no real number solution. a. For the equation to have one rational number solution, the discriminant b squared minus 4c must be equal to 0. b squared minus 4c equals 0. Negative 8 squared minus 4 times 3c equals 0, Replace a with 3, b with negative 8. 64 minus 12c equals 0, simplify. Negative 12c equals negative 64, subtract 64 from both sides. C equals negative 64 over negative 12 or 16 over 3, divide by negative 12. To check whether 16 over 3 will make the equation 3x squared minus 8x plus equals 0 to have one rational number solution, we have to substitute this value for C in the equation. 3x squared minus 8x plus 16 over 3 equals 0. 9x squared minus 24x plus 16 equals 0, multiply both sides by 3. 3x minus 4 squared equals 0, factor. 3x minus 4 equals 0, apply the square root principle. 3x equals 4, add 4 to both sides. X equals 4 over 3, divide both sides by 3. Thus, 4 over 3 is the only solution. B. For the equation to have two real number solutions, b squared minus 4c must be greater than 0. b squared minus 4c greater than 0. Negative 8 squared minus 4 times 3c greater than 0, replace a with 3, b with negative 8. 64 minus 12c greater 0, simplify. Negative 12c greater than negative 64, subtract 64 from both sides. C less than 64 over 12 or 16 over 3, divide by negative 12. C. For the equation to have no real number solution, b squared minus 4c must be less than 0. b squared minus 4c less than 0. Negative 2 minus 4 times 3c less than 0, replace a with 3, b with negative 8. 64 minus 12c less than 0, simplify. Negative 12c less than negative 64, subtract 64 from both sides. C less than 64 over 12 or 16 over 3, divide by negative 12.
We need to find the nature of roots of the following quadratic equations. Note that we've been asked only for the nature of the roots and not values of the roots. The first thing we need to know is that for the quadratic equation ax squared plus bx plus c equals 0, the roots are given by this formula. And the nature of the roots depends on this value, which is called the discriminant. If it's greater than 0, then the quadratic equation will have two distinct real roots. If it's equal to 0, then the quadratic equation will have equal real roots. And if it's less than 0, then the quadratic equation will have no real roots. Keep this idea in mind. Let me solve the first one for you. The first thing we need to do is find the values of a, b and c. Comparing the first equation with the general form, we get the value of a as 9, b as negative 12 and c as 4. Now it's easy to calculate the value of b squared minus 4ac. It will equal negative 12 squared minus 4 times 9 times 4. Negative 12 squared is 144 and 4 times 9 times 4 is also 144. So we get the value of the discriminant as 0. What does this tell us? It tells us that this quadratic equation has two equal and real roots. Try solving for the roots and verify your answer. Now I want you to try finding the nature of the roots of the second question. Comparing the second equation with the general form, we get the value of a as 2, b as negative 9 and c as 4. What will be the value of b squared minus 4ac then? It will equal 49, which is positive. This quadratic equation will have two distinct real roots as its discriminant is positive. And you should be able to solve the third one easily. We get the value of the discriminant as negative 7. This quadratic equation will have no real roots. You should try solving the above equations to verify your answer, and it's a good chance for practice too.
Roots and coefficients of quadratic equations. The sum of the two roots r1 plus r2 is equal to negative b over a. Roots and coefficients of quadratic equations. The product of the two roots r1 times r2 is equal to c over a. Relation of roots. 1. The sum of the roots is the additive inverse of the quotient of b and a. 2. The product of the roots is the quotient of c and a. Examples. A. Determine by inspection the sum and product of the roots of the equation x squared minus 3x minus 28 equals 0. Based on the given equation, a equals 1, b equals -3 and c equals -28. R1 plus R2 equals -b over a. Equals negative times -3 over 1. 3 equals 3. Check. R1 plus R2 equals -b over a. 7 plus -4 equals negative times -3 over 1. R1 times R2 equals c over a. Equals -28 over 1. Equals -28. Check. R1 times R2 equals c over a. 7 times -4 equals -28 over 1. -28 equals -28. The roots of the equation are 7 and -4. B. Write the equation in standard form 2x squared minus 4x minus 1 equals 0. Thus, a equals 2, b equals -4 and c equals -1. Solution. R1 plus R2 equals -b over a. Equals negative times -4 over 2. Equals 2. R1 times R2 equals c over a. Equals -1/2. The roots of the equations are 2 plus square root of 6 over 2 and 2 minus square root of 6 over 2. Check if the sum and products are correct. R1 times R2 equals -b over a. 2 plus square root of 6 over 2 plus 2 minus square root of 6 over 2 equals 2. 4 over 2 equals 2. 2 equals 2. R1 times R2 equals c over a. 2 plus square root of 6 over 2 times 2 minus square root of 6 over 2 equals -1/2. 4 minus 6 over 4 equals -1/2. -2 over 4 equals -1/2. -1/2 equals -1/2.
Now, in this video, what I want to show you is how the roots of a quadratic equation are related to the coefficients of the quadratic equation, and also how we can build up other quadratic equations with roots based around these roots. So, if we're given a quadratic equation ax squared plus bx plus c equals 0, where a, b and c are constants, and that quadratic equation has roots alpha and beta, then clearly we could say that this came from the factorized equation x minus alpha times all of x minus beta, that equaling 0, which would lead to x equaling alpha and x equaling beta, the roots of the quadratic equation. Now if we expand this, we end up with x squared, and then for the x terms, if we factorize at the same time, we're going to get minus x alpha and minus x beta. So if I just put alpha plus beta there in brackets times x, that gives us our x term. And then we've got minus alpha times minus beta, which is going to give us plus alpha beta, and this will equal 0. Now when it's put in this format, notice how the quadratic equation that we started with turns out to be x squared minus the sum of the roots times x plus the product of the roots, and that equals 0. And so this is something that we're going to be coming back to many times over, that any quadratic equation can be expressed in terms of its roots then as x squared minus the sum of the roots times x plus the product of the roots, and it equals 0. Now if I number this first quadratic equation as 1 and then this one here as 2, if I divide through equation 1 by a, let's just put a note here, divide equation 1 by a, then we get x squared plus b over a times x plus c over a, and that equals 0. Now if I compare this equation to equation 2, let's just put it here, compare with 2, what do we notice? What I notice is that minus all of alpha plus beta must be equivalent to b over a. And the product of the roots, alpha beta, must be c over a. So what we have then is, in summary, this result. Sum of the roots, alpha plus beta, equals minus b over a, and the product of the roots, alpha beta, equals c over a. Now, here I have a typical kind of question you're likely to get based on these results. We have the quadratic equation x squared minus 3x minus 5 equals 0 has roots alpha and beta. And we've got to find the quadratic equation with roots alpha squared and beta squared. So going by this result here, if our roots are alpha squared and beta squared, then the quadratic equation that we're going to be looking for is x squared minus alpha squared plus beta squared times x plus alpha squared beta squared equals 0. So we're going to need to work out first of all then the sum of the roots, alpha squared plus beta squared. So let's just put that down there. We're going to need to know that result. And for the product of the roots, well, that's going to be alpha squared multiplied with beta squared. Now, in order to get these values here without physically getting the roots, what I can pick up on is this idea here. We know that the sum of the roots, alpha plus beta, okay, equals minus b over a. b is negative 3, a is 1, so we're going to end up with 3 divided by 1, in other words 3. And we can also get the product of the roots, alpha beta. We know that alpha beta equals c divided by a, so in other words minus 5 divided by 1. Minus 5 divided by 1, and that's going to give us minus 5. Now, to get alpha squared plus beta squared, what we need to do is turn to an identity, and that identity is alpha plus beta all squared. Alpha plus beta all squared, if we were to expand that bracket, is alpha squared plus 2 alpha beta plus beta squared. So I can get alpha squared plus beta squared just by simply rearranging this. If I take 2 alpha beta away from both sides, I end up with alpha squared plus beta squared then will be equal to alpha plus beta all squared minus the 2 alpha beta. And that's nice because I've got the value of alpha plus beta and alpha beta from up here. So in other words, alpha squared plus beta squared then will be alpha plus beta, which we know is 3, that's all squared, minus 2 times alpha beta, and alpha beta was negative 5. So we've got 9 plus 10, in other words 19. And to get alpha squared beta squared, all we need to do is just say that this is all of alpha beta all squared. Alpha beta we see is minus 5, so we end up with minus 5 all squared, which is 25. And so we now can say that therefore the quadratic equation that we're looking for, just put an intro here, the quadratic equation, what's it going to be? Well, it's going to be x squared minus the sum of the roots times x. We know that the sum of the roots is 19, so it's going to be minus 19x, and then it's plus the product of the roots, which is 25. So you've got plus 25, and that equals 0. So we've been able to develop this quadratic equation based on the roots of this quadratic equation without physically finding out what alpha and beta were. Out of interest though, if you were to work out alpha and beta, you'd have to use the quadratic formula to get those values. And if you did, this is what you'd get. Alpha turns out to be 4.192 and so on, and beta turns out to be minus 1.192 and so on. And I leave it up to you to check by using the quadratic formula what the roots of this quadratic equation are, you should find you get 17.577 and so on, and 1.422 and so on, which turn out to be the squares of these two values respectively, alpha and beta. Now in my next video, what I'll be doing is showing you how you can build up more quadratic equations from the reciprocals of the roots here and the cubes of these two roots. Very common questions that you're likely to get, so I would certainly encourage you to have a look at that and try those examples. Okay, well I hope that's been then of some use to you so far.
Quadratic equation given a pair of roots. Example A. Write a quadratic equation given a pair of roots 7 and -2. Solution. 1. Reverse the factoring method using the solutions 7 and -2. X equals 7 or x equals -2. X minus 7 equals 0 or x plus 2 equals 0. 0 factor property. X minus 7 times x plus 2 equals 0. Multiply the factors. X squared plus 2x minus 7x minus 14. Simplify. X squared minus 5x minus 14 equals 0. Example B. Write a quadratic equation given a pair of roots -square root of 5 and square root of 5. Solution. 1. Reverse the factoring method using the solutions -square root of 5 and square root of 5. X equals -square root of 5 or x equals square roots. X minus square root of 5 equals 0 or x plus square root 5 equals 0. 0 factor property. X minus square root of 5 equals 0 times x plus square root 5 equals 0. Multiply the factors. X squared plus x square root minus x square root 5x minus square root of 25. Simplify. X squared minus 5 equals 0.
Greetings, M squared. We are going to write quadratic equations if they tell us what the roots are. Remember, roots, x-intercepts, solutions, zeros, those are all the same. But they're telling us our x-intercepts or our roots are -3 and 4. So it's kind of like working backwards. So what I know is that x equals -3 and x equals 4. And if you remember from solving by factoring, that's what you ended up with. But the step before was when you solved each one for 0. So if I add 3 to both sides here, and I minus 4 from both sides here, I get x plus 3 equals 0, and x minus 4 equals 0. And where did those come from when we're working backwards? Remember, they were in the parentheses after we factored, and so it was like an x plus 3, x minus 4, and then we set each factor equal to 0. So we're just kind of working backwards. Now we just need to use FOIL. Well, the first's x squared, then I get plus 3x minus 4x minus 12 equals 0. But these are combinable, so I get x squared minus 1x, 3 minus 4 is x, -x, minus 12. So here is a quadratic equation that has the roots -3 and +4. So let's try this one. Again, we'd have x equals -5 and x equals 1/4. To move things to this side, we just add 5 to both sides, and we get x plus 5 equals 0. Notice I don't want to just add a 1/4. I want to get rid of that fraction. So to get rid of the fraction, I'd multiply both sides by 4. So now I'd have 4x equals 1, because those would cancel out. And then that's when I minus. So that's plus -1 for both sides. So I'd actually get 4x minus 1 equals 0. So now these are the two factors that I had set equal to 0 if I was solving it. So I put them back in the parentheses, and then I use FOIL to find the equation. X to find the quadratic form of the equation, not the factored form. X times 4x is 4x squared, plus 20x, my inners, my outers, minus x, my lasts, -5. So if I simplify combining like terms, I get 4x squared plus 19x minus 5 equals 0. And that is the quadratic equation. So if you remember how to do it the way where you start with this and factor and go back, just kind of remember all the steps in reverse order, and you will get a quadratic equation that has those same roots. Good luck with that. M squared, signing out.
Equations transformable to quadratic equations. A quadratic equation is not always in the form of x squared plus bx plus c equals 0. In fact, there are times when we have to form an equation just to see whether it is in fact a quadratic equation. For example, the equation x equals 3 plus 18 over x may not at first appear to be a quadratic equation. However, clearing fractions and transforming the resulting equation gives us x squared minus 3x minus 18 equals 0, which is obviously more recognizable. If the quadratic equation is not in this form, we can perform whatever operations are necessary to transform it to this form. Some possible operations are any of the axioms or properties we have developed for transforming equivalent fractions. A partial list would include the following. 1. Clearing of fractions by multiplying all terms by the LCD. 2. Removing the parentheses and other grouping symbols. 3. Removing the radical signs by squaring both members of the equations. 4. Collecting like terms. Solving quadratic equations. Example 1. Express the following quadratic equations in standard form. Write the equation with a positive coefficient for the second degree term. Solve. A. 10 over. Solving quadratic equations. Solution. B. 7 times x squared minus 9 equals x times x3. 7x squared minus 63 equals x squared minus 3x, use distributive axiom. 6x squared plus 3x minus 63 equals 0, collect like terms. 6x plus 21 times x minus 3 squared 0, factor. 6x plus 21 equals 0 or x minus 3 equals 0, equate each factor to 0. X equals negative 7 over 2, x equals 3. Use the principle of zero product. Circa 4 over. Solving quadratic equations. Solution. D. Square root of.
Solving equations transformable to quadratic equations. Number 1. X times the quantity of x plus 5 equals 14. So what we're going to do here first is we're going to distribute x. So we're going to have x times x. This will be x squared. And x times 5 is 5x. Then this is equal to 14. Then we're going to transpose 14 to the left side. So we're going to have here x squared plus 5x minus 14 equals 0. Then solving this one using factoring, we're going to find factors of negative 14, in which if we're going to add a 2, the answer will be 5. So the factor will be 7 and negative 2. So 7 times negative 2 is negative 14. Then 7 plus negative 2 is 5. So we're going to have here x plus 7 times the quantity of x minus 2. Then this is equal to 0. Then in here, using the zero product property, we can have here x plus 7 as x plus 7 equals 0, and x here is equal to negative 7, and in here x is equal to 2. So this will be your answer. Now to check if your answer is correct, we'll just substitute these values of x here in the original equation. So checking, we're going to have here if x equals negative 7, so we're going to have negative 7 times the quantity of negative 7 plus 5 equals 14. Then negative 7 plus 5 is negative 2, so we're going to have negative 7 times negative 2 is it equal to 14. Then negative 7 times negative 2 is 14. So your answer here is correct. Now if x is equal to 2, we're going to have here 2 times the quantity of 2 plus 5 equals 14. So 2 plus 5 is 7, so we're going to have here 2 times 7 equals 14. Then 2 times 7 is equal to 14, so 14 is equal to 14. So the answer is correct. Number 2. Quantity of s plus 6 squared equals 9. So what we're going to do here is apply extracting the square roots. So we're going to extract the square roots of both sides. We're going to have square root of s plus 6 squared equals square root of 9. Then square root of the quantity of s plus 6 squared, this is equal to s plus 6. Then square root of 9, this is equal to positive negative 3. Then we're going to have here s equals, transposing 6 to the right side, negative 6 plus minus 3. So we're going to have here two solutions. So s here will be equal to negative 6 plus 3, and or s equals negative 6 minus 3. Then negative 6 plus 3, the answer here is negative 3. Then in here, s will be equal to negative 9. Now for your checking, again, we're going to substitute these values of s here in the original equation. So the original equation is s, or quantity of s plus 6 squared equals 9. Now if s is equal to negative 3, we're going to have here negative 3 plus 6 squared equals 9. Negative 3 plus 6 is 3 squared, and that will be 9. So the answer is correct. And if we're going to have the value of s equals negative 9, so we're going to have here negative 9 plus 6 squared equals 9. The negative 9 plus 6 is negative 3 squared equals 9. Negative 3 squared is 9. So your answer here is also correct. Number 3. Quantity of x minus 2 squared plus quantity of x plus 3 squared equals 25. So we're going to operate this 2 here first. So x minus 2 squared, that will be x squared minus 4x plus 4. Then plus, this is x squared. Then x times 3 is 3x times 2 is 6x. Then square of 3 is 9. Then this is equal to 25. Then x squared plus x squared here, this is 2x squared. Negative 4x plus 6x is 2x. Then 4 plus 9 is 13. This is equal to 25. Then transposing 25 to the left side, so this will become 13 minus 25. And 13 minus 25 is negative 12. So we're going to have here 2x squared plus 2x minus 12 equals 0. Then in here, the numerical coefficients of x squared and x, and also the constant, which is negative 12, is divisible by 2. So we can just divide the equation by 2 so that we can simplify the equation. So 2x squared divided by 2 is x squared. Then 2x divided by 2 is x. Then negative 12 divided by 2 is negative 6. Then this will be equal to 0. Then solving this one using factoring. So we're going to find factors of negative 6, in which if we're going to add a 2, the answer will be 1. So the answer here will be 3 and negative 2. So we're going to have here x plus 3, then times the quantity of x minus 2. Then in here, x will be equal to negative 3, and in here, x is equal to 2. And to check if our answer is correct, we're going to substitute negative 3 and 2 to x in the original equation. So if x here is equal to negative 3, so we're going to have negative 3 minus 2 squared plus negative 3 plus 3 squared is it equal to 25? So negative 3 minus 2 squared is negative 5 squared, is 25. The negative 3 plus 3 is 0, squared is 0, equals 25. Then 25 plus 0 is 25, so you're going to have the correct answer. Then if x is 2, so we're going to have here 2 minus 2 squared plus 2 plus 3 squared equals 25. And 2 minus 2 is 0 squared, so 0. 2 plus 3 squared, that will be 5 squared, is 25. So you got the correct answer. Example number 4, 6 over y plus y minus 3 over 4 equals 2. So first, we're going to simplify or eliminate the denominators by multiplying the equation by 4y. Then 4y times 6 over y, that will be 24. Then 4y times the quantity of y minus 3 over 4, so cancel 4. So we're going to have here y times the quantity of y minus 3. Then this is equal to 4y times 2 is 8y. Then this is 24 plus y times y is y squared. Y times negative 3 is negative 3y. Then this is equal to 8y. And 24 plus y squared minus 3y. Then transposing 8y to the left side, we're going to have here negative 8y equals 0. Then combining the 2 here, this is negative 11y, and arranging terms, we're going to have y squared minus 11y and plus 24 equals 0. Solving this one by factoring, we can find factors of 24 in which the sum of the two is equal to negative 11. So the factors will be y minus 8 times the quantity of y minus 3. This is equal to 0. Then y here is equal to 8 and y here is equal to 3. So this will be your answer. Then to check if your answers are correct, just substitute the values of 8 and 3 to y in the original equation. So checking, we're going to have here 6 over, if y is equal to 8, then plus 8 minus 3 over 4 equals 2. Then 6 over 8, we can just simplify this one as 3 over 4. Then plus 8 minus 3 is 5 over 4 equals 2. Then 3 plus 5 is 8 divided by 4, that is equal to 2. So 2 is equal to 2. Then if y here is equal to 3, so we're going to have 6 over 3 plus 3 minus 3 over 4 equals 2. Then 6 divided by 3 is 2. Then 3 minus 3 is 0, divided by 4 is 0. Then 2 plus 0 is 2 equals 2.
Solving non-quadratic equations. There are certain equations that are not really quadratic but can be thought of in such a way that they can be solved as quadratic. For example, consider this fourth degree equation. A, x to the 4 power minus 7 x square plus 12 equals 0, given. X square square minus 7 times x square plus 12 equals 0, let u equals x square. U square minus 7u plus 3 equals 0, substituted to the equation. U minus 3 times u minus 4 equals 0, factor. X square minus 3 times x square minus 4 equals 0, substitute x square for u. X square equals 3 or x square equals 4. X equals positive or negative square root of 3, or x equals positive or negative 2. To check solutions in example A. First note that when x equals square root of 3, x square equals 3 and x raised to the 4th power equals 9. Also, when x equals negative square root of 3, x square equals 3 and x raised to the 4th power equals 9. Similarly, when x equals 2, x squared equals 4 and x raised to the fourth power equals 16, and when x equals negative 2, x squared equals 4 and x raised to the fourth power equals 16. For positive negative square root of 3, x raised to the fourth power minus 7 x squared plus 12 equals 0. 9 minus 7 times 3 plus 12 equals 0. 9 minus 21 plus 12 equals 0. 0 equals 0. For positive negative 2, x raised to the fourth power minus 7 x squared plus 12 equals 0. 16 to 7 times 4 plus 12 equals 0. 16 to 28 plus 12 equals 0. 0 equals 0. The solutions are 2, negative 2, square root of 3 and negative square root of 3. B. X squared minus 2 squared minus x squared minus 2 minus 6 equals 0, given. U squared minus u minus 6 equals 0, let u equals x squared, 2. U minus 3 times u plus 2 equals 0, factor. U equals 3 or u equals negative 2, use the principle of zero products. Now, substitute x squared minus 2 for u and solve these equations. X squared minus 2 equals 3 or x squared minus 2 equals negative 2. X squared equals 5 or x squared equals 0. X equals positive negative square root of 5 or x equals 0. Check, note that when x equals positive negative square root of 5, x squared equals 5. For positive negative square root of 5, x squared minus 2 squared minus x squared minus 2 minus 6 equals 0. 5 minus 2 squared minus 5 minus 2 minus 6 equals 0. 9 minus 3 minus 6 equals 0. 0 equals 0. For 0. 0 minus 2 squared minus 0 minus 2 minus 6 equals 0. 4 plus 2 minus 6 equals 0. 6 minus 6 equals 0. 0 equals 0. The numbers square root of 5 and negative square root of 5, and 0 satisfy the original equation. Hence they are solutions.
To summarize our topic, the radicand b squared minus 4ac in the quadratic formula is called the discriminant. We can determine the number and type of solutions of a quadratic equation by evaluating the discriminant b squared minus 4ac. First, if the discriminant is greater than 0, the equation has two real solutions. Both will be rational if the discriminant is a perfect square or irrational if otherwise. If the discriminant is equal to 0, the equation has only one solution, which will be a rational number. Third, if the discriminant is less than 0, the equation has no real number solution. In terms of the relationship of the roots, the sum of the roots is the additive inverse of the quotient of b and a. That is, the first root and the second root is equal to negative b over a. The product of the roots is the quotient of c and a. That is, root 1 times root 2 equals c over a. A quadratic equation is not always in the form ax squared plus bx plus c equals 0. In fact, there are times when we have to form an equation just to see whether it is in fact a quadratic equation. If a quadratic equation is not in this form, we can perform whatever operations are necessary to transform it to this form. Some possible operations are any of the axioms or properties developed for transforming equivalent equations. To derive the quadratic equation, when the two roots are given, subtract each root from x to get the corresponding linear factors and equate the product of the linear factors to 0.
Activity. A. Fill in the blanks to make each statement true. B. State whether the roots of the following equations are real and unequal, real and equal, or imaginary and unequal. C. Write a quadratic equation with the given roots. And D. Solve the following equations.
I hope you guys learned from our topic for today, and I'll see you again on our next class.